Excellent.
Okay, all right. So I'm happy to be here with you, and it's kind of interesting, a little bit intimidating that we're getting close to the end of the semester, right? We have today 2 meetings next week, and then we'll have a review session / buffer / fun time on that final Tuesday before the reading days. Okay. So I'm grateful that you're all here and that we're still moving along. Okay, administratively, can you see your exam scores yet?
Yes.
Okay. All right. So we got an issue with at least one person not having taken the exam, so we're still holding off on giving back physical copies. All right. Hopefully, things will. We'll see what happens. All right. What was that? Question?
Not you.
Okay. Well. All right. Great.
You're good.
I'm good. Thank you. That feels nice to feel about good. All right. So that's going on, and yeah. So we have office hours Mondays, Wednesdays, and Fridays, and there's only a couple Mondays left. There's 2, and there's 2 Fridays left. There's 1 Wednesday left. If you want to have office hours during the finals period, that's fine with me. I can keep mine, and I think Raj should be going through this as well. Okay. All right, but come on in. We have a good time. For those of you who have attended office hours, I hope that you've enjoyed them. All right, so let's get going. Today we get to talk about failure criteria again. And the last time we were talking about 2 types of failure criteria. Any recollections? What were the 2 types of failure criteria that we discussed last time? Okay, kick it off.
Max shear stress theorem.
Okay, max shear stress theory, and that was for brittle or ductile? Ductile materials, yes, Chris. Okay, yes, Kevin.
Max normal stress.
Max normal stress, and that is for, obviously, the brittle materials. Okay? So what are we going to do today? We're going to do 2 more theories. 1 for brittle materials, and 1 for ductile materials. Okay? And the first one, when we talk about brittle materials, it's interesting. It's a little bit trickier. Okay. But the second one on ductile materials, that's the one that you're gonna see in all the finite element packages. Okay. Actually, finite element, like even in pre-po max, if you were looking at the types of stresses that you could observe, right? You have options for Tresca, and you have options for von Mises. Tresca refers to what we discussed for ductile materials last time. That's the, and then von Mises is what we're going to be looking at today. All right. Before we get to these great theories, though, first we're going to cover safety factors. Okay? These are deceptively easy, okay? Because I get confused on them, and well, maybe it's just me, okay? But you might find them deceptively simple, okay? And then we'll get into a criterion for brittle materials. That's called the Moore criterion. And then we'll get into maximum distortion criterion for ductile materials, okay? So, what do you guys think of when you hear factor of safety? In the okay, go ahead. You can say maybe in the mechanical sense or the non-mechanical sense. Yes?
Like an extra cushion to.
Yeah. It's your extra cushion, right? We have a buffer. We have our last day of no planned material because that's our cushion. That's our buffer, right? We didn't know what could happen during the semester. Right? And we've been fortunate that we've been able to do stuff, right, without too much impediment. Okay. So what else? How else do you all think of safety factor? Overrated? Overrated, like safety factors are overrated? Okay. I don't suggest that in your interview for an engineering position, you say, that one's overrated. That's overrated, really. We just go for the leading edge, right? We just go for the leading edge, and if it fails, it fails. Yeah, that's probably not a winning strategy, okay? Okay, so, like we're talking about this cushion, right? If I'm going from College Ave, if I'm going to College Ave to Livingston, right? How much time do you put in there? What would you estimate? 20 minutes? Okay, College Ave to Livingston. All right, fine. 20 minutes. And then how much variability? So that's how much time you estimate, but if you want to be on time, how much of a buffer do you put in? Another 20?
Well, with these buses, they suck.
Yeah, I double up the time for these buses.
Okay, so you double, so you just do, so you would say 40 minutes as a safety? Okay, now, so if that's 40 divided by 20, that's a safety factor of 2. Now, Cook Douglas to Livingston.
That is like
Okay.
That's a danger.
Okay, but I hear danger, right? Okay, Cook Douglas to Livingston.
Are you talking about the beginning of the semester or in the middle of the semester?
Let's say first week.
It'd be faster to walk.
It would be faster.
It would be, okay, so and then how much, so let's say you say an hour. Do you still say 2 hours, or do you put even more on top? For like a buffer? Hour? Hour and 30? Okay, so that'd be 2.5 hours divided by 1 hour. That would give you a safety factor of 2.5. All right? So depending on the conditions, right, what you are trying to accomplish, your safety factor is going to change. Do not design for less than 1 though. Right? Safety factor of 1 is it will barely make it. Right? So like that's like me showing up late to class. Right? Like if I have a safety factor of 1, I probably will show up late to class. Okay? And this semester I've actually been a lot better than in some of my other semesters. Okay? Maybe I got a little smarter with my safety factors. All right? So we are going to specify in the mechanical realm, we're going to specify that our forces, our torques, our stresses, they're supposed to be less than some allowable amount. Okay? And we can think of the ratio of this amount that we're specifying that it's better than, that's like the allowable, and what we have, or what the loading actually is, that ratio, we can think of as a safety factor. Okay, so another way to look at it is, this is the force that's going to cause the system to break, and I'm going to tell you, you better not go above a certain amount. Okay, so like, if you're making a table, and you know that table actually will break at 300 newtons of force on top of it, but on the instruction manual you say do not load to 200 newtons, right? That's 300 divided by 200. That's a safety factor of 1.5. Yes, Chris C, but not that one. Not zero. Yeah. Sorry, I'm not supposed to say that. Did you hear that, Chris?
Wait, what? Can't say that.
Well, I don't want you to do your identity, right? You want your identity?
So like in thermodynamics we have like quality as like a factor, and that's supposed to be like between 0 and 1. Is there like a range for factors?
Yes, I'm glad you asked that. Good foreshadowing. Okay, so if you're doing an aerospace project, okay, your safety factor is going to probably be less than if you're doing a more conventional product for a mechanical system. And why would that be? Why do you think you would use a lower safety factor with a lot of aerospace systems, if you look at the mechanical systems. Okay? Yes.
Like people can die in aerospace.
But when I'm using lower safety factors, so does that mean that there's more probability of death? Yeah, okay, Juan?
You need it to be light.
Yeah, so you need it to be lighter for many aerospace systems because you gotta get it off the ground, right? You know, I can make a nice little cage for a mouse, and make it really heavy, right? So the aircraft or the plane or the rocket will never get off the ground, right? So, you know, there's absurdity, right? But there's also practicality. So typically what happens is in aerospace, you're thinking 1.25 to 2 as your safety factor, and some systems maybe it's less than 1.2, but it's got, you know, that's close. Now, how do you know, you can also think of safety factors as a fudge factor. The lower the safety factor, right, that means the lower the uncertainty, right? You're more certain about it. So you're going to do more testing, more simulation, more understanding of the environment, okay, and maybe more inspection as well. So in aerospace, you've got to do inspection, right, for practice, okay? But they're trying to save money, right? You can't get from point A to point B and burn more fuel than you would like to, right? It's very expensive, okay? So, and then mechanical systems, right? You know, you're typically thinking like 1.5, 2, 3, right? And safety factors have come down in general because we're better at understanding what the effective stress in a structure is through experience, through simulation. Okay? So here are some different ways to think of safety factors. Safety factor could be a force, okay, when it fails. So this could be something akin to the yield strength times cross-sectional area. Okay, that would give you a force at failure over some force that's being allowed, right? So this is what you anticipate or specify the force that you can handle might be. Okay? Another way to look at it is in terms of the stresses. Okay, so you can think of this as the stress at failure, right? So that's where you would plug in, you know, sigma y, your yield strength, right? Or you might plug in your shear strength, okay? And divide by what your strength, what your load is, right? And here's the shear form. Okay, so we're going to do larger than 1 for these, okay? Now, have any of you ever broken anything? Okay.
Chalk.
Huh? Chalk. Yeah, last time, yes, Jeffrey, we did. Jeffrey, we did bring some chalk last time, right? So, often, right, the whole structure doesn't fail all at once, right? That would be like a wonderful design, right? It's like you've got it perfectly set up so that when you put that load on, it just like all breaks. Right? Would that be wonderful? No, so, you know, as a designer, as a mechanical engineer, you're going to be looking for the hot spots. And you're going to be beefing up those areas and making sure that the system is able to handle this. So this is, if you think about the F fail and the F allow, right, that's more like a global thing, right? But then you're also looking at what the local stresses are. So another way to think of the safety factor is as what your stress fail would be up, divide by your operating stresses that you anticipate. And as we were saying here, the wording can be confusing. Okay? You'll see that, I think, in a minute. I don't think I have to say much more about that. The wording can be confusing, all right? But we can change your safety factors, obviously, by either lowering the allowable load or increasing the maximum stress, okay? And if you want to look at a fun, thought-provoking video, all right, you can learn a little bit about planned obsolescence. Okay, so are you familiar with this term at this point? You all probably are at this age in your generation. Planned obsolescence?
What is it?
Planned obsolescence.
No, you already in the groups here.
Okay,
I don't.
okay. So, is it in a company's best interest for you to buy one product from them and never buy another product from them?
Oh, plan failure?
Yeah. No. What?
Uh-huh. Right? What? Yes? So, is it their best interest?
Like the Ford and like car manufacturers back then.
Okay. Yeah, so,
Car breakdown.
right. All right, what else do you replace every few years? Huh? Tires, yes, tires, yeah, so like you might, if your tire's not as strong as you could, right? So that they have to come back and buy them again. Not that they refuse it, okay, but it's an idea, all right? And Chris, this one was talking to me this phone, all right? Right, the older cell phones, right, they lasted for a while. Now we have dates when we know they're no longer going to update the security things. Okay? Good day. But instead, right, it's planned obsolescence. Okay, let's keep going. I'm going slow. So here's the example for now. Very similar to the one we did before. Okay? We're saying that we have a brittle material, all right, and we're going to use the criteria of maximum normal stress with a safety factor of 3, okay? All right, so let's look. What do you all think? Is this one going to be okay? If we say we have to have a safety factor of 3, how does the maximum normal stress in the system compare to the ultimate tensile strength? It's a safety factor of 2, right? Does that mean that we have a safety factor of 3? No. Does that mean that we're satisfying safety factor of 3? No. Right? So we can go through, you did it brilliantly, okay, in your head. This is not too hard, right? We're saying that the maximum normal stress has to be less than the allowable, right? And what is the allowable? Well, we can write out the factor of safety equation. We say sigma fail over sigma allowable is equal to the safety factor, right? What is sigma fail here? 100 megapascals, right? Okay, what is Fs? Fs is the factor of safety. They're saying that needs to be 3. So what does that make this allowable stress? 33 about, right? 33 and a third. Okay? So you put it all together and you now know that your allowable stress is 33 megapascals. Okay? And that is not greater than the sigma 1. So you're gonna have to. Okay, see how this works? No, okay, what's the question? Everything? It's
I
okay.
actually don't understand the 50 MPa. Where does it define what it is?
Okay.
Professor, it's just that, I'm so sorry,
Yeah.
it's just that the result, if it's less, that's the result, that's correct, that's what you're saying.
Right. So if we go above the allowable, we have an issue that it's going to break, right? Or we're not. It may not break, to be honest, right? But it doesn't satisfy the specified maximum, all right? Which is based on the safety factor, right? That allowable is the max that we are going to withstand. The 50 megapascals, this is an element. We did this last time. We actually had the same exact box. This is a uniaxial loading, all right? Meaning this is an element that has just sigma x or sigma y or sigma z, right? In one direction. So sigma 1 is equal to 50 megapascals, sigma 2 is equal to 0, and sigma 3 is equal to 0.
So this is the current pressure it does.
This is the current stress. This is the state of stress on an element. Okay? Right? And so that's why, and we gotta think, right? So you've got a whole structure maybe, and you're like, I'm looking at all these different spots, and I'm trying to make sure that in this particular case, I take one or I take a lot of them, and I gotta make sure that my stress that I have at that spot is less than the allowable. Okay? Let's look at this one. So in this case, we've got a shear stress of 30 megapascals. This is more subtle, right? Why is this more subtle? Well, we have to think, what criterion are we using? Maximum normal stress, right? So what is the equivalent maximum normal stress here? Yeah, right, you're right, it's still 30 megapascals, right? Okay, but we had to do the, at least I would do more circle here, right? And we look at it and it's still the same stress. So now sigma 1 is a normal stress, okay? Sigma 2 if you want could be minus 30 and sigma 3 would be 0, okay, in this case. Okay, so now the same question, is sigma 1 less than the allowable? Yes, right, it is. So will we have failure? No, but this is okay. All right, so no failure. That's happiness. All right. Now let's look at another one. Okay. What does this one look like? What does the Moore circle for this one look like? I have to, that's hard to do in your head, right? That one's hard to do in your head.
22.5.
Okay, so let's look.
Negative.
Okay. Do you agree with this? That we plot the 30 and the 15, right? That's this point right here. Okay? And it turns out that the sigma y, like if this is x and this is y in that direction, right, in the bouncy direction, then that's 0, right? So that's going to be here. That's where we're going to be crossing, because that would be 180, right? So now we got to figure out, all right, if we rotate over to here, right, that's where the maximum stress is going to be. So let's look at it. Sigma 1 is going to be what? It's going to be 15, right? That's the average, right, is 15, right? The average between sigma 1 and sigma 2, right? Sigma 1 plus sigma 2 divided by 2, that's just 15, because sigma 2 is 0. So that's where we are, or sigma y, sorry, sigma y is 0, I should say it like that. So sigma x plus sigma y divided by 2. That's that, okay? And then here, this is at an angle of 45 degrees, okay? Because this is 15 here, and this, okay, is out here. So then we can say that the length that we're going to have over here, okay, is going to be 15 squared root of 2, and then we add it to the average, and that's how we get 36. So 36 is not less than the allowable, okay, which means that we will have failure. All right. So what I'd like you to do, okay, is take a minute and look at this one. This is your first homework problem, okay? And then after you've taken a look at this one, there's another one too. But take a look at this one, all right? So your numbers are different, okay, than mine, all right? But you have a sigma x, and you have a minus some type of negative sigma y, okay? And the other stresses are all equal to 0, okay? And now the question is a little bit flipped, because it's asking, what is the safety factor? Okay, according to the criterion of maximum shear stress. Shear stress, if the yield strength is 200 megapascals. Okay, so this is a little bit tricky, right? No, it's not? Okay, so if I give you a yield strength of 200 megapascals, let's look at it this way, because we're using maximum shear strength criteria. If I give you a yield stress of 200 megapascals, what is the maximum shear stress that that material can handle? What is the maximum? So if I say, here's the, yes, go ahead. Okay, so if this is the yield stress, I hand you this material. Yeah, there you go. It's a piece of steel or a piece of aluminum, and it has and either one of them could have a maximum yield strength of 200 megapascals. I ask you, without you looking at this element, without looking at this configuration of stuff going on, what is the maximum shear strength of this material? No. I said the yield strength is this. You tell me how much shear can it handle?
The ratio is sigma x and sigma y over
Okay, let's take a moment on this, all right?
so 15, 25.
Does someone, while I'm taking a moment, does someone want to blurt out the answer? Not to the whole problem. My question is, does someone want to blurt out the answer to my first question? My first question is, if I give you or sometimes we write it as what's the maximum shear strength of the material? Yes. No, that's I love that equation. That's for maximum transverse shear stress on a beam under loading. Okay. But no, that's not what we have here. Yeah, it's half. It's half. Why is it half?
I have no idea, I just remember other equations. Yes. It's a good question. Yeah, I just remember it.
No. Okay, back it up, guys. It's hurting. It's hurting. Okay, so if someone tells you the yield strength of the material, how was that yield strength calculated? Or how was it measured? How did you measure it in your lab?
You're getting the elastic module and
Making the
strain.
intention.
Right. Okay. So you had some yield force, right? And you had some area, right? Okay. And so the sigma y was just the force at yield divided by the cross-sectional area. Right? That's the cross-sectional area. Okay? It was loaded uniaxially. All right? So that's sigma y. What does the state of stress look like? Now I'm just drawing the material element. That's the state of stress on a uniaxially loaded member, idealistic. So what does the Mohr circle look like here? For uniaxial stress, what is the Mohr circle?
Zero and sigma y.
Yeah, 0 and sigma y, that's it, right? Right? I've got my sigma y out here. Okay? And my sigma 2, so this now is my sigma 1, right? So sigma y, right? And sigma 2 and sigma 3 are equal to 0, right? So what's the maximum shear stress that I can have? Right, the maximum shear stress is down here, right? Right? And that's going to be okay? Any questions on that? So to even start this homework problem, right, you probably want to think about what is the maximum shear stress the material can handle. Okay? So now we know that's the maximum shear stress the material can handle, right? What is now the So let's go back. Back. Yeah, okay, can you see this? Yes. Okay, so that's the maximum shear stress the material can handle. What is the maximum shear stress now in the part? Right? That has to be calculated carefully. If I told you, so we've got this element. This is 100 megapascals. This is 50 in the negative direction. Okay. What does the Mohr circle look like here? So you got one over here that will say that's minus 50, right? We've got one out here that's at 100. Oh, sorry, you're supposed to be seeing something. Let's see if I can make it available. Hold on. Yeah, okay, now can you see? Okay. All right, here we go. Okay, so this, right, is saying that we have a sigma 1. What is the sigma 1 here? Yeah, so we'll say this is sigma 1. We could call this sigma 2 or sigma 3, the negative 50. Okay, all right. And then what's sigma 3 in this case? 0, right? Okay, so what am I have multiple Mohr circles, right? So I have this Mohr circle, I have this Mohr circle, right? And then what's the final one? It's the one that goes between sigma 1 and sigma 2. Or sigma 1, yeah, sigma 1 and sigma 2. All right? So then what's the max that I have here? Yep. Okay. All right. So we could call this is my operating if you want, tau op, right? And this is like my tau allow, or no, I won't say tau out, tau fail. Okay. All right. And what was it here? 1/2 SY, which was 100 megapascals. Whoops. Sorry, it was 200 megapascals. Right? So this tau fail is going to be 100 megapascals. So the safety factor is just going to be the tau fail divided by the tau op. Okay? And I think someone shouted this answer out already. What is 100 divided by 75?
4/3.
right? Which is
1.3333.
yeah. So it's just put down 1.3. Okay. Yes, Paul. Okay, so you're asking about this equation? Okay, it's because when I have uniaxial loading, when I calculate the yield strength, it's only in one direction. Sigma 2 and sigma 3 in this case are 0. But I need to know the maximum shear strength. Right. So for a lot of these problems, for some problems, you have to construct a Mohr circle to know what the stress, the stress at failure is, so that you can compare that stress at failure to the stress during actual operation, or the allowable stress. Okay? Any questions on this? Okay. Yes. Okay, so if this is SY right here, do we agree on that? So what's this down here? Half. Is that okay? Is that right? Okay. No. I mean that's fine. Okay. There were crickets a few minutes ago, so I guess there are multiple people who have had this question because there wasn't an immediate response. Yes, Kevin.
In all situations, is the yield strength equal to twice the maximum shear stress then?
Yes.
In all situations.
Well, okay. If it's a specified yield strength, and I care about the maximum shear strength, yes, that ratio is as we've defined here.
But in this example, when you're only talking about shear stress, does that relationship still hold?
When we're talking, so in this case,
Because we were, yeah.
yeah.
So with stress and with strain, the relationship is unchanged.
Hold on a second. Stress and strain. Where does strain come into this?
I'm sorry, I thought you just said strain a second ago.
Oh, I'm sorry. I didn't mean to say anything about strain.
Okay.
I didn't mean to say anything about strain. Okay? If I said something about strain, it slipped.
Sorry.
Okay, this is all about stress.
So the yield stress is always equal to twice the maximum shear stress.
Yes.
Okay.
For this, for uniaxial loading, right? Okay. Okay. Okay, but we'll get into some situations in a little bit where it's a little bit dicier. Okay, where you got to think a little bit about. Well, we'll just get into them, and then I'll explain why it's a little bit dicier. Okay, you got to think maybe not just about what's happening with the yield stress or the shear stress, but you might think about the combo loading. Okay, and how if I increase both combos by the same factor, how that would affect a safety factor, right? Because in this case, let's just look at it this way. In this case, if I increase these loads, the 100, I'm not showing the right thing. If I increase the 50 and the 100 by the same factor, right? That is, so for example, if I increase them both by a factor of 1.3, in fact, right? If I were to do that, okay, then I would have 130 megapascals here and 1.3, what is 1.3 times? That's 65, right? About?
Yeah.
Okay?
No.
Yeah. Yeah, it's 65. 50 times 1.3 is 65. Okay, so if I do that, right, then what happens is my tau operating would be exactly equal to the tau fail. And then my safety factor would be 1. Okay?
So is there maybe a generalized procedure to find yield strength as a function of shear stress?
Well, no. This is just calculating the safety factor. What I'm talking about is now we're looking at whether or not something's going to fail. Your first question is valid. Okay, your first question is just about how does the yield strength relate to the shear strength? Okay, and yield strength has a very specific meaning because it's for uniaxial loading. Okay, and that maximum shear strength, all right, also has a very specific meaning. It's 45 degrees rotated, and that's going to be the maximum shear strength. When we start looking at things where we're just comparing shear strengths, okay, what we have to be careful, what I'm getting at is we have to be careful that you increase both of these proportionally, right? If I increase this by a factor of 1.5, but I leave this one the same, right, I'm going to get a different result. Okay, so often what you're looking at doing is you're multiplying both, okay, or multiples. You're multiplying the different stresses to figure out what the new effective stress is so that you can come up with a safety factor. Because the safety factor is just a number, right? But it's like, oh, if I multiply this stress by 1.5 and this stress by 1.2, right, that's going to give me something different. And that would be, you're going to have a different safety factor. That may not scale proportionally. Okay? Okay, let's go on. Okay, the next problem is about a beloved thin-walled pressure vessel. Okay? And in this case, all right, we're asking, it's a design question. Okay? There you might have to think about increasing the thickness of your pressure vessel to make sure that you get to an appropriate level of safety. All right, so that's safety factors. Like I said, simple concept, but deceptively so. As I mean. All right. Cartoons. More criterion for brittle materials. This is painful sometimes. Okay? I'll be absolutely honest. And this is wrongo. I didn't fix it here. Okay, that's just supposed to be 1 or minus 1. I fixed it in other places, but I didn't fix it there in the transition slides. Okay? So do you remember that we're supposed to use caution when thinking about brittle materials? All right, so this is old, going through it. Okay, and remember we were talking about how the breaking is due to maximum normal stresses, and when you have a brittle material, right? You remember this too? Okay. Now, if we have the criterion of maximum normal stress, okay, what we get is looking at, are we between the field goals? Right? You remember that too? Okay, and inside the box. Failure is outside the box. And something I didn't use this term last time we met, but you can look at this as an envelope. Okay, so if you're in the envelope, if you're within the failure envelope, you're okay. If you're outside the failure envelope, not okay. Okay. And we also talked about how the compressive strength is often bigger than the tensile strength. Okay. And I should have made this more clear. With the brittle materials, often we care about the ultimate tensile strength and the ultimate compressive strength because they break and fracture, or they yield and fracture essentially at the same time. Okay? So, the Moore's criterion addresses, it addresses the fact that this compressive strength is larger than the tensile strength. And remember we mentioned that? For brittle materials, that's often the case for the ceramics. So, when you have a difference in these, okay, you can get a value under tension, you can get a value under compression, and you could also get something under torsion if you want. Okay. The stress strain plot, or I'm sorry, the Mohr circle plot might look like something like this. Here is an ultimate tensile strength. Right out here. Again, we're assuming that the other two stresses, other two normal stresses are 0. Here is the compressive strength. Okay? So this had to be done from 2 separate tests, right? One case, you're pulling it apart. The next case, you're compressing it. And then the third test is a torsion test. And that means that your center of that Mohr circle is right on the middle axis, and it's a pure shear situation. What do? We look at these 3 Mohr circles, and we come up with what we call a failure envelope that goes around them, like this. And this failure envelope on a sigma 1, sigma 2 plot has some similarities to what we've seen before. If you're in quadrant 1 of the sigma 1, sigma 2 plot, guess what? Mohr circle out here, still pretty good. If you're in this Mohr circle, right, this quadrant 3 also pretty much resembles this. The weird stuff happens when you have sigma 1 negative, sigma 2 positive, and sigma 1 positive, sigma 2 negative. And the Mohr criterion says it looks something like a curve going between this point and this point, this point and this point. Okay? But we don't plot that curve, or we don't create an equation for that curve. What instead we do is create a linear approximation. Okay? And so this is kind of funny, right? Because you're like, wait a second, this kind of looks like the maximum shear stress criterion a little bit. Okay, because remember that we got those diamonds? Okay. But now we have a different compressive strength and a different tensile strength. So what we end up doing is we figure out what this line is. How do you figure out what this line is? How do you figure out what this line is? If you had to figure out that line, how would you go about doing it? Hint, hint. If you had to do this.
Good thing I don't.
That's a good thing you don't right now. What's that? Oh, no, okay, you're doing something else. All right, so, yeah, how do you figure out those lines? Yes? Yeah, right? Okay, so if I'm down here, right? Which one's my y-intercept?
Maximum tau.
It's going to be this one down here, right? Well, this is not a tau, right? This is sigma 1, sigma 2 plot, okay? There is a tau over here, right? But you're going to figure out this is sigma ultimate compression, right? Or negative sigma ultimate compression, right? In fact, this is missing. So these are, or it's positive the way this is done, all right? So these ultimate compressions, they would be negative, all right? And so that's a negative point here, okay? And then you can figure out what the slope is, right? Because you can figure out, you went over some sigma ultimate, right? And you rose some sigma ultimate again. You went over some sigma ultimate tensile, and you rose some sigma ultimate compressive. Okay, so you can figure out what the lines are, like this. Okay? And sigma ultimate compressive, this is assuming that this has a It's a negative value, so this is negative, negative, so it's going to have a positive slope, right? And sigma ultimate compressive, again, assuming it's negative, right? So that's going to be down here. Any questions on how you do this? On how you figure out what those lines are? Pretty straightforward, right? Okay. Now, and on the other side, you can write this like this. Okay. Okay. Let's look at an example. We're going to say that you have an ultimate compressive strength of 150 megapascals and a ultimate tensile strength of 100 megapascals. Okay? And the question is, for this state of stress, which we've seen before now, is it going to fail? And for this state of stress, which we've seen before, is it going to fail? Okay? And this is where I messed up. Okay, so let's look at what's going to happen. I'm not quite sure. Hold on, let's see. Okay, so for this one, sigma 1 equals 50 megapascals. Sigma 2 is equal to 0, which is equal to sigma 3. What are we going to do? How would you approach this? Yeah.
I would draw more circle, and then I would plot sigma 1 and sigma 2 on a sigma 1 sigma 2 plane,
Yeah.
and use the parameters that we got where the top right corner was sigma ultimate under tension, sigma ultimate under tension.
Yeah.
And I would just see if it is inside that
Yeah.
box.
Yeah. Okay, so in this case, for this one, it's probably easiest just to write down sigma 1, sigma 2 plot, skip more circle for now. Okay? Because then you only have normal stress, right, in your problem. And then draw this thing out using the linear approximation, right? When I say the linear approximation, that's these walls right here and right here. Okay? This is 100, 100 up here. Okay? And this is where we are. We're at 50, 0, right? And so it's pretty straightforward. It's less than this point. It's not going to fail. Okay? So that one's pretty straightforward. The safety factor, all right, that might be a little bit trickier, all right? But you can think of, if I multiply the safety factor times sigma 1, which is the 50, right? How does it relate to the ultimate tensile strength, right? So if I scale all the loads, the rest of them are 0, but I scale just that one load, right? How much can I scale it by and still be less than 100? I can scale by a factor of dos, okay? So I get safety factor of 2, okay? What about here? What am I going to do? Here, I have 30 megapascals, and it's a shear stress, okay? And I care about normal stresses. So in this case, I will go ahead and I will make it more circle, because I want to figure out what my principal stresses are in the system. Okay. What are the principal stresses? Well, we've done this before. They are going to be positive 30, minus 30. Okay. Those are the two principal stresses. Then I take those principal stresses and I put them on a sigma 1, sigma 2 plot. And I am in quadrant 4 because sigma 1 is positive and sigma 2 is negative. All right? And now my question is, if I'm in the envelope, I've got to be above or below this line. I got to be above that line, right? So if I'm in this region, I'm safe. If I'm over here, not so much. Okay? So how do you do that? How do you figure out if you're above or you're below? How would you do it? Go ahead.
I would plug 30 into sigma 1 for that equation for the line,
Yes?
and if sigma 2 is less than it, we're good, we're above it.
You're absolutely right, okay? So you have to be able to define the line, okay? And then you take your sigma 1 that you had, you put it into the equation, you figure out what the sigma 2 is on the line, and if that is below this value, you're good, okay? So we do that. The sigma 2, we'll call it line, all right? So if you're at 30, let's say we're at 30, this is down, that point right there is at minus 105. Okay, see that? And we have, in actuality, right, we have sigma 1 and sigma 2, we have 30 comma minus 30, so that's going to be way up here. Okay, like up there. Okay. Now, so what do we know? We know we're safe, right? Everyone agrees we're safe? How do we figure out the safety factor? How do we figure out the safety factor? And Kevin, this is where I was saying, this is where it gets a little bit tricky. Okay, so how do we calculate a safety factor? So we need a safety factor times a sigma 1 essentially, okay, to go outside of the envelope. All right? And if we're multiplying, okay, we had this, right? And we have this, right? This is what we've got, right? We need this to go outside the envelope. Okay, there's an interesting thing that happens here. Right? So we're here, and what is it going to take for us to hit this line? That's the question. That is the question. What's interesting here, right, is if I multiply sigma 1 and sigma 2 by the same factor, right, they go along this line. What's the slope of that line? What's the slope of the purple one?
Is it opposite?
Orthogonal?
Well, no, what's the slope? Just a number. I want a number. What's the slope?
The inverse of the other one. The negative
Guys.
inverse of the.
Isn't it the safety factor?
What's the slope of the original?
No, they're not orthogonal. Okay, they're not necessarily orthogonal. Okay? For one, what is the slope of the purple line?
-1.
Thank you. Thank you. You were going to say that, right? Yes. It's -1. No, I was talking to the guy up there. I can't remember your name. But yes. Okay. So, look. This, when you scale the loads, you scale all the loads on the element. All right? And we know from our experience with Moore's circle over here that as I scale sigma 1, sigma 2 goes the opposite direction, all right? And they both go together, and we have a slope of -1, right? So if I scale them both by 2, right? Then this becomes 60 and this becomes -60, right? It's going to be on this line. So the question is, when do I go outside? Okay? And I've got this relationship, sigma 2 is equal to minus sigma 1. So here we are. We have an equation for the green line right here. And we have an equation for the purple line. And we ask ourselves, where do they intersect? That is a linear combination problem, right? Right? Except this is kind of trivial. Well, not that trivial, but I don't have a plus b over here, or plus c or plus d or whatever. Okay? So we can go ahead, substitute, right? So in this case, take the sigma 2 is equal to minus sigma 1, plug it in, and figure out what sigma 1 is. They intersect when sigma 1 is equal to 60. And that means that sigma 2 will equal minus 60, right? And so now we know that we have a safety factor of dose. Okay? Are there any questions? this is not trivial, in my opinion. All right? This requires thinking through things a little bit. Okay? And understanding that now, when you're thinking about a safety factor, it's a quantity, right? That you're multiplying everything by. Right? And that it's going to affect all the stresses. Yes, Paul.
So I can see how you made the 1.50 comma 0 on the left. So, like, why are you creating that 2 points? The second one being the 30 negative 30. Like, I get where the 30 negative 30 comes from, but like, I'm struggling to wrap my head around what you did.
Yeah, the reason I use 2 points is because I have 2 normal stresses here, right? For the second problem. Here I only had 1 normal stress. So if I think about scaling the stresses, all the stresses, the only thing that scales is sigma 1. So this point is just going to move along the horizontal axis.
So those are 2 different scenarios?
Yeah, they're 2 different scenarios.
Okay.
Right? It's 2 completely different scenarios. Okay? But they both seem to have a safety factor of 2. That's a nice coincidence. Okay. All right, let's keep going. You guys have a question, okay, that you can work on, but we don't have much time, so we gotta keep going. All right. But this question, okay, will allow you to get a little bit of experience using this new criterion, the Moore's criterion. For calculating out whether or not there's going to be failure. Okay, part 3 in our act, okay, is looking at what happens with ductile materials. And this criterion is going to be something that you see in your career, all right? If you do anything where you're looking at breaking or yielding materials that are ductile, this is the one, okay, that everyone uses. So let's define a couple things. We're going to say applicable to ductile materials, okay? And this was first done by Hoover in 1904, but also known as the von Mises criterion. Okay, also known as the Maxwell-Hoover-Henke von Mises criterion. Okay, so a lot of people got involved. There's one guy's name that's not in here, Tresca. Okay, Tresca, maximum shear stress. Okay, Henke, Hoover, von Mises. Who am I forgetting? Maxwell. This theory. Okay, is distortion of space. Okay? So remember this nice little plot. U is strain energy. Okay? And that is the area under the triangle. And what is that? It's been a long time. That's a stress strain curve. Remember those? If you go all the way back, right? But that's how you figure out the elastic modulus, for example, right? The slope of this line, the purple one, right, that's the elastic modulus. So, you're like, duh. A material undergoes change in shape or volume with elastic loading. We agree on that? Yes. Do we also agree that we can store elastic energy within the material? Yeah. All right. All right. If it's in the linear elastic regime, all right, it comes back. We have problems when we go beyond the elastic limit, right? And here's where the interesting kicker happens. For a ductile material, we say that under hydrostatic loading, it will not fail. Okay, so what does that mean? That means if I take a piece of metal that's ductile and I drop it in the ocean, and it sinks and it keeps sinking and it keeps sinking, the pressure keeps building up. The pressure is the same on all 6 sides if it's a cube, all right? or it's the same on whatever shape it is, that piece of metal, if it's ductile, is not going to break. Is that interesting? Kind of, right? It's kind of interesting, right? Okay, so sigma 1 is equal to sigma 2 is equal to sigma 3. It's only when you have differences in the principal stresses that you get distortion, and that causes there to be the. Okay, so that's what these guys came up with. It's distortion. When you get distortion when there's shear. So this is related to maximum shear stress, right? The stress cut. Okay. Now you don't have to care about this too much, or the last part where there's like equal stresses on optic equal. Don't worry about that. All right. But what we're going to do is we're going to go through derivation pretty quickly. First, we start with strain energy density. Okay. Then we think about this state of triaxial stress where you would only have principal stresses, and then you calculate a strain energy density. Okay, you remember? So you get this? Where we gone? So this was one-dimensional. This is three-dimensional. And sigma 1, sigma 2, and sigma 3 are quantities. Okay, they don't have to be equal here. All right? And there's no shear stress in this particular orientation. Then, Hooke's law. All right? You remember that one? That's fun. Okay? And what we're going to do is we are going to we're not going to think about epsilon x, epsilon y, epsilon z, but we're going to think about epsilon 1, epsilon 2, epsilon 3, okay, and sigma 1, sigma 2, sigma 3. And we can write out these relationships, all right, where we have epsilon 1 is equal to this, all right, and then we have sigma 2 and all this, right? We can write things out where if we multiply now, okay, by a 1/2 sigma 1, we get this expression. Okay? That's kind of a weird one, right? Where did that come from? That's a little bit weird, right? But it mathematically makes sense. So then what do? We substitute in, okay, these expressions, all right, into our strain energy. Okay. Right? You see this? This is 1/2 sigma 1 epsilon 1. That's 1/2 sigma 1 epsilon 1. And so we can substitute that in. We can substitute in the equivalent for the sigma 2 epsilon 2, right? We can substitute all these in, and this is the expression that we get. After we do this substitution, okay, we can think about the hydrostatic components of stress. What is that saying? If sigma 1, sigma 2, and sigma 3 were all the same, right, and I added them all up to each other and I divided by 3, I just get sigma 1 or sigma 2 or sigma 3, right, if they're all the same. If they're different, I am looking for the mean. And I'm going to say that's the hydrostatic stress. Okay, I'm not looking for the average. Okay. Then, what are the distortional components? The distortional components of stress are not that mean stress, but they're the difference between sigma 1 and the average, the difference between sigma 2 and the average, and the difference between sigma 3 and the average. Right? So I've come up with like this. This is the average stress. These are the differences in the 3 different directions. And these are causing distortion. And we go back to an earlier assumption that yield is going to result from distortion. So when we do that, okay, we plug in, okay, these expressions, right? So we have a sigma 1 over here, right? We can plug that in. We have a sigma 2 over here. We can plug that in. We plug all this stuff in, okay? And this is the expression we get. This is the strain energy due to distortion, okay? So UD is not the same as U, okay? but this is the strain energy due to distortion. Okay? So now, once I've come up with this expression, okay, we can think about what happens in uniaxial loading. What happens in uniaxial loading? Sigma 1 is equal to something, sigma 2 and sigma 3 are not, they're equal to 0. Okay, they're equal to 0. And we can figure out what the strain energy is due, or what strain energy we expect at yield, because we can plug in the yield strain. See that? We plug in the yield strain, and now we have a strain energy due to distortion at yield. So, failure happens, in this case, when the specific strain energy due to distortion exceeds the specific energy due to distortion at yield. Okay? So if I have a material and I pull on it and I apply and I get too much distortion energy in it, that's when it's going to fail. Okay? That's when it's going to yield. So now what you can do is you can do some equation. You can equate some of these things to each other. This strain energy, right? And this strain energy. Okay? Strain energy at yield, right? And you can say there's going to be an equivalent uniaxial stress, okay, for a given state of loading. All right, this is a little bit wild. Okay, it's kind of like saying, hey, you know what? Before I could figure out what an equivalent maximum shear stress was, right? Remember that? That was the maximum shear stress theory. Okay, I figure out, okay, this is the absolute maximum shear stress for a given state of loading. Now we're saying this is the equivalent uniaxial stress. And this is what we compare to the yield strength. Okay, so remember we had a factor of 2 business that was not so fun? What we're saying now is you can calculate out what the uniaxial stress, effective uniaxial stress is, and compare this directly to the yield strength, the sigma y. Okay? So what you do is you compare this, to sigma y or sy. Okay? And if the uniaxial stress is greater than sigma y, you have a failure. Any questions on this? Yes?
What does it look like when you draw uniaxial stress, I don't know, on a foam shaft?
Yeah, so this is what you'll see, all right, is that at every, so imagine you had a phone, okay, like you said, right? You have a phone. And you have, at every location on a phone, you calculate sigma 1, sigma 2, and sigma 3. I then say, look, I now have one number, one stress. That's the equivalent. That's the sigma uniaxial. That's what your finite element software does, right? Your finite element, if you click on von Mises and you see the colorful plot, it's calculating out the von Mises stress. And then you just think about it in terms of how does it compare to the yield strength, okay? So here's some takeaways. And you want to write both of these on your equation sheets, okay? These two. This uniaxial stress is using, well, actually, you guys tell me, what's the difference between this one and this one? What's the difference between the top equation and the bottom equation? Paul? Yep, I agree. So the bottom equation is give me the state of stress. Come as you are, right? Come as you are and plug it in, and I spit out an equivalent stress. The top equation means that you've already done some work or you already have a principal state of principal stress. So the top one is really useful when all you have are normal stresses, because that's the state of principal stress. So you just use sigma 1, sigma 2, sigma 3. The bottom one is very useful if you have a box with shear stresses, right? And you don't want to use more circle. You could use more circle, right? To figure out what the principal stresses are and then use the top one. Or you can just plug it into the bottom. Okay, so you want to have both. Okay? And if it's a plane stress situation, it turns out that this is the envelope. Okay, this is the envelope that you have on a sigma 1, sigma 2 plot, okay, based on the yield strength. What does that mean? The envelope, okay, I'm running out of time. Okay.
Oh my God.
Okay, I'm going to jump through this. The envelope looks like this. Okay? This is what the envelope looks like. It's an ellipse, okay? And it goes with a diagonal like so. All right? We're out of time, so as you're doing this, I suggest, if you like, before the next time, take a look at the video. I go through much more detail on this in discussing what this line of pure shear is and what these different points are on them and how they compare. Okay? And then you've got a couple problems that you can look at for examples. Okay. And you can also look at the comparisons between these different criteria. Okay? Great. So what did we cover today? We covered safety factors, Moore criterion for brittle materials, and maximum distortion energy criterion. And what I'm going to do now is flip over to everyone's favorite part. Okay. All right. Please make sure you upload. And thank you. Yes.
Is there like an expected time? Boy, I think it's tomorrow. You said tomorrow.